Today let us talk about the Gauss Seidel iterative method. So for the Gauss Seidel iterative method, we find that for the Gauss Seidel iterative method, unlike for the Jacobian whereby we split A into D minus N, for the Gauss Seidel we split A into D minus E minus F, where we see that we see that D is a diagonal matrix which is written in that way. E is a lower triangular matrix also written in that way. However, these are negatives. Yeah, the negatives are there. These are also upper triangular matrix. Those are negatives. So you find that now from our problem, from my ax equals to y equals to b, now A, instead of writing that, I'll write D minus E minus F, where this is x and this is equal to b. So I can write that my dx equals to b plus ax plus fx. However, when we change into the iterative form, this is going to be d k plus 1. This is e. Now the interesting bit is this is also depending on the new value, current value. However, fx depends on the previous value. This is plus b. But I need this in the general form. So I have to make this x power into k plus 1. So this is going to be d minus e of xk plus 1 equals to fxk plus b. So therefore this is like xk plus 1 equals to d inverse d minus e inverse f xk. You have to respect the multiplication. This is d minus e inverse b, something like that. Something like that. So what do we do? So you find that, so I have my expression already in the form of b. Can write gs xk plus, now this is f, gs meaning Gaussian, that is the general iterative form, where this part here is that and this part here is equal to that. Now for convergence, earlier on we have tried to emphasize that if an iterative method is consistent, then it is convergent if and only if the maximum of the eigenvectors, let's say b, I will use this g of s, must be less than 1. However, in this case it's a different case. We can, however, computing BGS and finding its eigenvalues. For those who don't know about the spectral radius, this is like the maximum of the magnitude of the eigenvalue where these eigenvalues for I, which can be 1 up to n, which can be 1 up to n, and these eigenvalues that you see are like eigenvalues. This is an eigenvalue of B, BGS. So we can conclude on the convergence if the iterative form is consistent, and then it is convergence if and only if the maximum of the eigenvalues of B are less than 1. However, you find that this is a little bit complicated, so what do we resort to? So to simplify everything, we can also conclude on the convergence of this kind of iterative method using theorems whereby we are looking in terms of diagonally dominant, diagonal dominance, symmetric, and positive definite. Okay, so before I talk about the convergence, let me first talk about this iterative method that arises from the Gauss Seidel iterative method. So we introduced the parameter, just like we have just like we have the Jacobi over relaxation. So you find that in this case my xk plus 1. So you find that the general iterative method is written in this way. For the SOR, it is written in that way, and the omega can be 0, omega can be 1. When omega is a 1, that's when we have the special case of the SOR, which is what we call the Seidel iterative method. And if omega is 0, this really doesn't make sense, because xk plus 1 will just be equal to xk. Okay, however, you find that this omega can lie in the interval 0, 1, 0, 2. Yeah. Sometimes you can find our omega in the interval 0, 2, which is okay. Now back to convergence, where we talked about that we can try to define or try to explain convergence using the iterative methods, ignoring the aspect of the values, which sometimes can be very complicated to deal with, and we look at the diagonal dominance. And we base on that. So if I do the convergence, I can express this, the SOR iterative method, in this form. So therefore this will be xk plus 1, and this is equal to, let's bring the omega, so this will be omega d minus e inverse f plus this is I minus 1 minus omega, but this entire thing is times x plus omega into d minus e inverse b, something like that. Then we can proceed to convergence. A matrix A, which is in Rn, is said to be diagonally dominant by the column if the diagonal element is strictly greater or equal to the summation of all the other elements in the row. However, it can also be with respect to, so you find that they are said to be diagonally dominant by the row if all j equals to 1 up to n, that if this is greater or equal to a summation that this is j and this is I. So, however, we can say strictly diagonally dominant by the row. Strictly diagonally dominant by the row if this is just greater. Even here I can say strictly diagonally dominant by the column if this is just greater. Okay, so we can have an example. So for example, if I have my matrix A, so you find that with respect to row 1, the diagonal is the one which is greater than the magnitude of 2 plus 0. With respect to row 2, the diagonal entry 2 is greater than the 1 plus the 0. However, I can put the magnitudes. Then as I continue row 3, even here the diagonal matrix for 6 is greater than, this is 3 plus 2 magnitudes 5. So meaning that A is diagonally dominant by the row. And therefore we have a theorem which says that if a matrix is diagonally dominant, if matrix A of a system is diagonally dominant by the rows, then the Jacobi and the Gauss Seidel converge. So meaning that if I have my problem linear system that I want to solve and I check and A is diagonally dominant by the rows, then it implies that I can use either the iterative, the Jacobi method, or the Gauss Seidel method. One of them will converge, meaning we shall find the solution for the linear system. Then I can also try to explain a symmetric matrix. Matrix A is said to be symmetric if A transpose equals to A. So that's what they mean by a symmetric matrix. Then what do they mean by a positive definite? Positive definite matrix so it's said to be positive definite matrix if all its eigenvalues are positive. If all its eigenvalues are positive. So then we can also conclude on the convergence of the iterative method we are going to use. And in this case, they say that given that the matrix is symmetric and positive definite, then the SOR converges if W, now the parameter, is within 0 and 2. Okay. Hence, therefore, if A is symmetric and positive definite, then you expect if you use the SOR iterative method, it will converge, given that omega is in this. You remember the SOR has omega which can take on values 0, omega can be 1, and when we have this, that is when we have the GS, meaning this can also work. So if your A is symmetric and positive definite, then it is better you use the Gauss Seidel method, iterative method. So thank you. We shall do some MATLAB probably next time and some questions which are involved in this. I wish you got the best. Thank you. Have a good night. Please like and subscribe.